So the expanded version of the M&M game is actually available already on YouTube. So hopefully everybody has access to some M&Ms. There are no peanut M&Ms because I'm not sure what people's allergies are. And so this was, as I said a few moments ago, this was inspired by a question my son asked me a few years ago when he was 4. If two people are born on the same day, will they die on the same day? Now, as a mathematician, there are many ways to prove that two people don't die on the same day just because they're born on the same day. My wife's an identical twin. I will let you figure out what kind of experiment I could do. I would get into trouble with the police for actually doing this, but it would be a proof that two people born on the same day do not die on the same day. So how else could we attack this problem? And so it actually leads to a lot of phenomenal mathematics. And so I was actually able to use this question at the college level, and the solution in some sense involves hypergeometric functions, involves some really great mathematics. Rather than going straight to the M&M game, some people might want to have their lunch digest before they go to dessert. Let's talk about a simpler game. I am happy to date myself and say I will use my basketball players Larry Bird. Who do you think the other one is?
Robert Parrish.
I'm sorry?
Robert Parrish?
Nope, I need somebody from the Lakers.
KJ. Magic Johnson.
Magic Johnson.
Magic.
So Larry Bird and Magic Johnson are playing a game of basketball. First one to make a basket wins. Okay? And as a mathematician who has a lot of friends who are in economics, I don't mind making unreasonable assumptions. So I will make the following assumptions. Larry Bird has a percentage of getting a basket. It's P. It is always P. He never tires. He never needs bathroom breaks. He will always shoot a percentage P. Magic Johnson always shoots a Q. So Bird, basket, with probability P. Magic, with probability Q.
Are you applying those two probabilities?
And they're independent. They're independent.
Q is often used as the
Exactly. Q is often
P,
used as the
so
complement of P. And so here I want P and Q to be just two different probabilities. And this is a great time to talk about notation. Better notation might be P sub B and P sub M for Bird and Magic, or P1 and P2. And will that help students follow things a little bit more? As soon as you write Q, and I was hoping somebody would call me on this, people start thinking about certain things. Is there a relationship between the two? And in real life, there could be. You could feel the pressure to make a shot or miss a shot. So I'm going to just use P and Q right now. I'm used to doing it that way. First basket wins. And who gets to shoot first? Come on, in this room it should be clear. Larry Bird, of course. We're in Boston. Oh, close enough. Bird shoots first. So let's let X denote the probability Bird wins. So probability Bird wins, we'll call that X. And let's figure out what X is. So he can either win on his first shot, on his second shot, on his third shot, on his fourth shot. So what's the probability he wins on his first shot? P. All right. Now, what's the probability he wins on his second shot? I'm sorry? It's independent. It's independent.
not P and P.
Almost.
Not Q. P.
So if he actually gets to the point where he's taking his shot, then yes, the probability at that point of winning is just P. But what's the probability that he wins the game on his second shot?
Oh.
That's a different question than what's the probability he makes the second shot. The probability he makes the second shot is P, but he's got to get there. So what's the probability he wins the game on his second shot?
Does Magic get a shot?
Of course.
In there? Okay.
So I might not have said this, but they alternate. We have some notion of fairness. Bird shoots, Magic shoots, Bird shoots, Magic shoots, and they keep going until the first one to make a basket wins. You never get to shoot two in a row.
So not P and not Q for the first round.
1 minus P, 1 minus Q.
And then making it the second round, so P.
Okay. What about the probability that he wins on his third shot? Miss, 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 hit. Right? And so the first misses is 1 minus P 1 minus q, 1 minus p, 1 minus q, p, etc., etc., etc. Let's define R to be 1 minus p, 1 minus q. So it's the probability that they both miss. So now I can rewrite this as x is equal to p plus rp, and then what does this equal? R squared, because we had 2 misses. And the next term? And we just keep marching down the line like this. So we get x, I can pull out the p, is 1 plus r squared plus r cubed times p. Now, if you knew the geometric series formula, you would be done. I claim we can use this as a backdoor way to prove the geometric series formula. And when I teach, I actually bring a basketball net to my class. You know, it's a one-time business expense. My kids love the fact that I have it in my office. And by kids, I mean both my actual children as well as my students. And we actually play games of hoops. And so I ask for 2 volunteers at the start of the lecture. And I don't tell them ahead of the time, but the 2 volunteers each get excused from 1 homework problem for volunteering. And I actually make them shoot and see what happens. I'm going to show you another way to calculate this. This is a big theme in all the stuff I'm doing today. Calculate something 2 different ways and notice they're the same. Alright? So let's calculate x another way. So what's the probability Bird wins on his first shot? P. Right? Yeah, look at that. Now, assume Bird misses and Magic misses. What's the probability Bird and Magic both miss? 1 minus p times 1 minus q, or what we're calling r. Now, here's the trick. Given that Bird and Magic have both missed, and Bird now has the ball in his hand, what is the probability that Bird wins from this point onward? That's the probability he wins on this given shot. What's the probability from this point onward that Bird wins? X. Why X? That's what we defined it as, right? One of the hardest things in mathematics is proofs by definition. The answer is X because this is what we defined X to be. I remember spending very frustrating 2 hours as a freshman on a problem before I realized, oh, wait a minute, that's just the definition of what it is. The problem isn't that bad. Here, the whole meat is that the probability that Bird wins from this point onward is X. It doesn't matter that Bird and Magic have both missed. Now, in the real world, if you've been shooting for 5 hours straight, do you think you're still making a basket at the same probability as when you start? No. Extrapolate it outward to 3 days of nothing but shooting baskets. Eventually, they're going to be so tired they're not going to be able to. We're not in that situation. Larry Bird and Magic Johnson are perfect spheres. It helps with some other things. They're happy to keep shooting baskets without ever tiring. And so, in this unrealistic situation, we've reached the point where once they both miss, we've returned to the initial game state. All right. Well, now we've got x is p plus rx. We can solve for x. And so this implies, if we bring this over, 1 minus r times x equals p. So x equals 1 over 1 minus r times p. And here's the geometric series formula. These 2 expressions have to be the same. I've calculated the probability Bird wins 2 different ways. So this is a proof of the geometric series formula. Now, when you use the geometric series formula, what do you have to be careful about? If you're a mathematician and not a physicist or an engineer.
Denominator just never 0.
Denominator is never 0. A little bit more than just never 0. So when is the geometric series formula valid? So we've just shown that 1 plus r squared equals 1 over 1 minus r.
Your initial value is 1.
So if my initial value wasn't 1, I would have to tweak things. And so you could have the geometric series a plus a times r plus a times r squared, and that would put an a on both sides. So you're right, we're only doing a special case here. But what must be true about R for this formula to hold? So somebody give me a nice integer. 3. 1 plus 3 plus 9 plus 27 equals 1 over 1 minus 3 equals negative a half. So if you sum all the powers of 3, you overshoot infinity, come back from negative infinity, and almost make it back to 0 and stop at negative half. Okay. Something should hopefully be wrong here, right? I'm summing infinitely many positive numbers that are getting larger and larger and larger, and I'm getting negative a half. I don't need to have too much math background to know that this is not right. And the resolution is not the fact that Bird and Magic do not tire. What is wrong with using the geometric series formula here? So who's taught the geometric series formula to their students? So what do you have to check before you use it?
It converges.
So what makes it converge?
I think it's R less than 1.
So you need the absolute value of R to be less than 1. If the absolute value of R is not less than 1, the series diverges. If you look at the financial meltdown that happened a couple of years ago, there were many reasons for it. A lot of it was government intervention. A lot of it was people in banks using math formulas in places where they weren't justified to use them, where some of the assumptions were not met. And so to me, this is one of the greatest lessons you can have, is show your students something like this. And you have a reasonable formula, but you have to know when are you allowed to use it. And here, I can only use it if the absolute value of R is less than 1. If it's not less than 1, my series is going to explode. So if you think about the basketball game, what can you tell me about this number R? Where does R live? What are the possible values? Could R be 3? No. What's the smallest R could be?
Well, just about
Just about 0.
Have more faith in Larry.
0.
Could be 0. Bird's really good. Maybe Bird would never miss.
Oh, 100% success.
Right? So if P or Q is 100%, R could be 0. So what's the largest R could be? 1. Now, if R is as large as 1, this game will never end. Right? If Larry Bird and Magic Johnson can never make a basket, then it'll just go on and on and on forever. So you actually see this breaking down in the extreme cases. So this is between 0 and 1, and it gives us a good lesson. Test extreme cases. Try to get a sense of what's reasonable and what's not reasonable. If you want, for next Monday's class, for next Tuesday's class, I can give you 4 formulas to think about in the intervening week. One of the 4 formulas does a really good job of describing the probability that one team beats another. Try to figure out which of the formulas it is. I'll try to email you that tonight. So here, if we look at extreme cases, we see that there's something wrong. And now, as long as R is between 0 and 1, my physical model makes sense. It still makes sense in the case when R equals 0. The game is just much easier to analyze. I don't have infinitely many terms. I have 1 or 2 terms. Yes?
So, back up for a second. Can you explain how you went to the green line there?
Sure. This is calculating the probability that Bird wins in another way. So first, for the Bird to win, he makes his first basket, or they both miss, and at this point onward, we've reset the game. So this is the key concept. We've reset the game. Once they both miss, it's like we've just started playing the game from this moment.
So it's like adding another round to your...
But if they both miss, does it really, there's no need to say the round actually happened.
Right.
So imagine you walk in and Larry Bird has the ball. You know the game hasn't ended because he's getting ready to shoot. Do you know how many times he's shot and missed? No.
Right.
But his probability of winning is the same from this point onward if it's his 4th time shooting, or his 10th time shooting, or his 1000th time shooting. So this is the key idea. Technically, this is what's called a memoryless process. And this is a huge idea in game theory in analyzing certain states. That it doesn't matter how I got to where I am, it just matters that I'm here. Did you have a question, Terry?
It's basically stating that each trial is independent.
Each trial is independent, and it doesn't matter how you got there. Any chess fans here? Okay, so then nobody can correct me if I'm wrong. I think in some versions of chess, if there's a threefold repetition of position in a row, the game is considered a draw. This is just so that all games will terminate. You know, otherwise I could do something ridiculous. I move my rook, call check, you move your king. I move my rook back, call check, you move your king. I move my rook, call check, you. And we could just do this forever. And then the game will not end. And then if the clocks are going, the game could be decided by, you know, whose clock runs out first. So I think in some versions of chess, they will consider the game a draw if there's a threefold repetition of position. Well, if that's the case, then it does matter how you got to a position, right? They're not all the same now. It matters how you got there. So if you're trying to analyze something like chess, it's not enough to just say, this is my board position. Have I had that position before? What other positions have I had on my way to there? In a situation like that, it's not memoryless. Here, this would be an example of memoryless.
So with the, can I ask about our standing between 0 and 1? Does that correlate? Because we teach very, very simple probability with 6th graders, and we emphasize no chance of 0,
Right.
full probability 1. Does that correlate with
When you said no chance of 0?
The
when there's no, when there's no chance it happens
the
0.
possibility is 0.
Right,
And
yes.
so does that correlate with that 0 and 1
So
in
here,
your example?
so if R equals 0, then that means either P or Q is 1. So at least, or both. So at least one of the plays is perfect.
Okay.
And so this is a little bit of a twist there, because R is not an event you're directly measuring.
Okay.
You're directly measuring bird shooting and magic shooting. And R is 2 of these things happening in a row.
All right.
But you know, for R to be 1, the only way R can be 1 is if both bird and magic miss all the time.
Okay.
And so if you observe 1, then you have perfectly enough plays.
Okay.
And they will... Now when I have my students do this in the class, I tell them, you know, we keep doing this until somebody gets a basket. And I ask them, what can you deduce? And normally the only things you can deduce conclusively are one person has a positive % chance of making a basket. You know, the person who's never made a basket, we don't know if he could ever make one. If somebody actually gets the basket on their very first try, it could be perfect. But if they miss their first basket, we know they're not perfect. But we can't really say more than that. So it's always a question of how much can you deduce from something like this. So this idea of having this memoryless system is phenomenal. How many of you teach calculus? So you've sometimes had integrals involving like sines or cosines, and you integrate by parts, I think, once or twice, and you get the cosine again, and you bring it over to the other side and you solve. That's this. So in calculus class, I call it the bring it over method. And you get the expression you want to solve on both sides of the equation, so you bring it on back. And as long as the coefficient in front of the x is not 1 both times, you win. If this was 1, well, then the only way that this could hold would be for that to be 0, and then I don't have anything useful. Because R is not 1, I have something useful. Well, what would it mean for R to be 1? Well, if R is 1, then P and Q are both 0. Now, if P and Q are both 0, I have to just analyze that directly. There's a small subtlety here. There's a difference between what I wrote here for my conditions and what we have on R. So what is the difference between my conditions and what I wrote about R?
Down there, R can be negative.
Yes, R can be negative. So there's no way people have negative probabilities of events happening. Okay? So this does not handle the case of R negative. This only handles the case of R positive. So can you come up with a compelling story to handle the case when R is negative? Fortunately, you know, there are tricks you can do, and you can modify this so it will work if R is negative. And so I will just show you the trick I don't have a good story. But imagine you have x equals 1 minus r plus r squared minus r cubed plus r to the 4th minus r to the 5th plus dot 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 dot. I really don't like writing negative numbers. Whenever I have a variable, if possible, I like the variable to be non-negative, and if I know it's negative, I will explicitly write a sign. So assuming the following is justified, if you can prove the geometric series formula for non-negative r, you also get it for the negative r. I group things. 1 plus r squared plus r to the 4th minus r plus r cubed plus r to the 5th plus dot dot dot. How can I figure out what this equals? What could I use to solve this?
Isn't that just the geometric series with r equal to r squared?
Yes. And this is horrible notation. So
Yeah,
I
it's a
equals
bad
r
way to
squared.
say it, though.
Yes, no,
With the ratio equal r
yes,
squared.
the ratio equals r squared. That's a much better way of saying it. And I'm not blaming you, that's how I would say it as well, with I. So ratio is r squared. What about this? And this brings up an issue I think that Kristen mentioned a moment ago.
R is your A value.
R is my A value, so I pull out an r, and I have the same geometric series again. So I would have r times 1 plus r squared plus r to the 4th plus dot dot dot. And so in fact, I notice, oh, I have the same geometric series formula. I can fact a little bit. I have 1 minus r times 1 plus r squared plus r to the 4th, like this. Well, now I use the geometric series formula. It's 1 minus r, 1 over 1 minus r squared. And now you have to remember 1 minus r squared is 1 minus r or 1 plus r. The 1 minus r cancels one of the 1 minus r's. And we get 1 over 1 plus r. And we should really write that as 1 minus negative r, because negative r is my ratio. This is more than you would want to do, I think, for students. I think you'd want to do just the standard proof for the geometric series formula. But if you had some really advanced students and they were looking for something to sink their teeth into for a real challenge, ask them, can you try to figure out how to prove the geometric series formula for negative r, given that you know it for non-negative r? You know, again, absolute value of r is still at most 1. I don't want to do anything silly. But if I stay in a situation like that, what can I do? Can I still get it to work? Do people know the standard proof of the geometric series formula? Let me give the standard proof, and then I'll move into the to the M&M problem, because everybody should have M&Ms. There is still a lone apple left. I will admit, I was the one who had the other apple. Well, this way I can report to Henry that we did have some healthy eating. Okay, so here's the standard proof. So let's let Sn be 1 plus r squared all the way up to r again. And the idea is to look at something very similar to Sn and observe a lot of cancellation. So if I multiply by r, 1 times r is r. And so I basically just shift everything down 1 unit. So instead of going from 1 to r to the n, I go from r to r to the n plus 1. And now I subtract. And I get 1 minus r times Sn, so I'm just factoring as I do the subtraction. And here notice everything in the middle cancels, and I'm left with just 1 minus r to the n plus 1. And so what do we get? Algebra settles. We get Sn is 1 minus r to the n plus 1 over 1 minus r. But I like to write it as 1 over 1 minus r minus r to the n plus 1 over 1 minus r. So while this is not nearly as much fun as having your students shooting basketballs, it is a better proof in the following sense. It allows you to handle finite series as well as infinite series. And it allows you to see the difficulties that happen if the absolute value of r is greater than 1. So this piece doesn't really matter what r is. This is some fixed number. Doesn't matter what n is. It's just fixed. Over here, as n grows, as I take more and more terms, if the absolute value of r is greater than 1, this explodes. If the absolute value of r is less than 1, then this goes to 0. So if the absolute value of r is less than 1, then the limit, as n goes to infinity, of Sn is just 1 over 1 minus r. And that gives you the finite geometric series formula. And from it, you have the infinite geometric series formula. So then the question might be, why do we care about stuff like this? So you can go talk about situations where you would model things like this. So waiting for success, waiting for failure. How many times do I have to wait before I will see some events? So this leads into a lot of probabilities. And so, if you've done probabilities, I heard some people talk about teaching statistics. You can have binomial distributions waiting for the first success. And you can try to calculate things like mean values. And so, if people are interested, let me know. There's actually a really nice way to calculate the mean of a geometric series formula if you know calculus. How many terms do you have to wait for your first success? What I want to do now is I want to shift to M&Ms. And the full lecture is online. I'm going to just give you the short version. If you want to watch the longer version, by all means, get my YouTube stats up. So as I said, Cameron was 4 years old. Kayla was 2. And he asked me one day, if you're born on the same day as someone, do you die on the same day? And so I am a huge multitasking professor. I do not believe in stupid questions, only stupid students. I don't believe in stupid questions. I believe all questions deserve an answer. But they also deserve an answer that's age appropriate. And so there's a limit to what I can explain mathematically to a 4 and a 2-year-old. So I created what I called the M&M game. And so in fact, Cameron was just invited to the birthday party of one of his friends. His friend's grandmother writes children's books, and when I explained this game to her, she loved it, but wished it was a little bit less violent. So the way it works is the following. We'll just do 2 players, Cam and Kayla, but in real life, Daddy gets to play as well. So they each start off with some number of M&Ms. And what they do is they flip a coin at the same time. And if your coin comes up heads, you eat one of your M&Ms. And if it comes up tails, you don't. And they had to keep track, and they had to write things down. So this was a way for me to get them to practice their writing and stuff like that. And so the question then became, what is the probability that Cameron and Kayla will run out of M&Ms at the same time? And trust me, my kids were very willing to play lots of versions of this game to get lots of data as to how likely were they to end at the same time. So we normally did 5 M&Ms with 3 players. We can just do it right now. So if we had, if we didn't have the hourglass, I would have you break up into groups of 2, take some number of M&Ms, start flipping fair coins, and just seeing what happens. In each of time, let's just say I gave you the prediction, you were all amazed how accurate I was, and you're all wondering, how was I able to so accurately predict that? So let's talk about how you would analyze this. So let's say they start off with K M&Ms. What is the probability of a tie? So one of the things that I think is worth emphasizing is you don't have to be able to solve every question you ask, right? And so just because I ask a question doesn't mean I have to be able to solve it. And I'm happy to have students earlier in their career just asking questions and numerically trying to gather data to support this. So if the students aren't able to write down and do all the algebra to solve this, what could they do?
Experiment.
Experiment, right?
Verbal solution.
Go home and play the M&M game with your parents. My daughter has created a modification of the Cheerio game. And in the Cheerio game, you eat if you get a tail. But the analysis is pretty similar. Okay? It's not quite as much fun, but it is healthier. So you start getting data. See what the data suggests. what are other questions you could ask, either about this game or about related games? Because that's what I want you to be doing. I want you to be thinking, what else could we do? What else could we investigate? What else could we study? So what's another question?
How many turns till sermons?
How many turns? Can I set aside 5 minutes to play this game, or should I block off half an hour? How long do I expect this to take? Other questions?
Do they flip at the same time or take turns?
I'll have them flip at the same time, because otherwise there could be fights. And when we played this game, we sometimes had to let them pick which colored M&Ms they get. I never got to pick. So you could, lots of other questions. You could
There's
ask,
like strings of different results, so what's the likelihood of, that's just coin flip probability.
coin flipping probabilities. So you could ask, what's the probability that you eat 2 M&Ms at the start of the game? What's the probability somebody has a maximum lead at some point of 3 M&Ms, given that you start with 5 M&Ms? What's the largest lead anybody ever has throughout the game? That becomes a very challenging problem to look at. What if you have more M&Ms? What if you have more people? So there's lots of questions you can ask. And again, I want students asking questions. I don't want students just going through algebra and just solving the problems you give them. I don't want them to be the bean counters. I don't want them to be the trained monkey. I want them to think, well, what would be a fun question to ask? What's something I have a chance of answering? And so I'm happy to explain how to solve this if people are interested. And to solve this, we'll take a detour into the Fibonacci numbers first. Okay? So at least one point, don't make it too obvious. Somebody please say aha so I can go home and just feel good that I've done my job. Okay. If anybody says it right now, it'll be too obvious. Fibonacci numbers. I actually did several research papers with students on the Fibonacci numbers. There's a lot of fun things you can look at. So they're given by the following relationship. Fn plus 2 is Fn plus 1 plus Fn. And then I need to give you a little bit more information. It's not enough to just say this relationship. I have to give you 2 values. It doesn't matter which 2 values I give you. The easiest is to give the first 2 values. F0 equals 0, F1 equals 1. Later, I will actually show you, if you're interested, a new definition of the first 2 terms, which is actually better for some advanced math applications. Once we have this rule, each term is the sum of the 2 previous, we can just generate all the terms in the sequence. 0 plus 1 is? 1 plus 1 is? 1 plus 2? So at this point, we can just start 34, 55, 89. You can just start generating them all. So once you know 2 consecutive Fibonacci numbers and you know the recurrence relation, you can get every single term. So we call this a recurrence relation or a difference equation. It has 1 index. The Cam-Taylor game it's going to turn out will have 2 indices, and that'll make it a little bit harder. So there's a lot more depth I can go into in the Fibonacci numbers. I'm not going to get into all the stuff right now. There's a limit to how much I want to do in the afternoon. I want to give you a sense of why you might care about them. So what's the canonical example people use when trying to motivate students to study the Fibonacci numbers? What do you talk about?
Nature.
I'm sorry?
Nature.
Nature. So we're in nature.
Rabbits.
Rabbits. So I think the biggest example is rabbits are breeding out of control in Australia, and we need to figure out how many rabbits there will be given the following. There's a lot of other applications as well. If you look at leaves on plants, the leaves that spiral around, they actually spiral in a Fibonacci pattern. And the reason is to maximize exposure to sunlight. So they go at what's called the golden angle. And somebody reminds me, I'll put a link to this. There's a beautiful Nature by Numbers video. Have you seen this one?
No,
Yeah, it's a wonderful video. Leaves on the bottom are bigger than leaves on the top. If you have just 1 leaf, it doesn't matter where it is. If you have 2 leaves, well, you'd want them diametrically opposite. But if you're going to be putting on more and more leaves, you don't want leaves covering up other leaves. You want to maximize your exposure to the sun. And so the plants actually have the leaves going at about 137-degree angle, which is the golden angle. It's related to the golden mean. The golden mean is related to the ratio of adjacent Fibonacci numbers. And this maximizes how much area you're going to expose to the sunlight. There's lots of wonderful applications of Fibonacci numbers in nature. And so if you're trying to motivate students as to why you might care about something like this, there's lots of things I can link to. I will give you a more interesting example. Las Vegas. So how many of you ever played roulette? I'm sorry?
I know you're not supposed to.
You're not supposed to. It's a tax on people who don't know math. What you want to do is you want to play against the other humans. You don't want to play against the house. So in actual roulette, there are 18 reds, 18 blacks, and 2 greens. And all of the numbers are allegedly equally likely to come up. We will consider a slightly easier version where there are 18 reds and 18 blacks. And you can only bet on red or black. You bet $1 on red, it comes up red, you win $1. You bet $1 on black, it comes up black, you win $1. If the other color comes up in what you bet on, you lose. So you've got a 50-50 chance each time of winning. The following strategy is called double plus one. How many of you have heard of double plus one?
I think I have.
Okay. Vegas loves people who've heard of this strategy. Because they feel that they can go and take Vegas's money. So I will show you a way that's guaranteed to win money in Las Vegas. And I have a nice video that I made with some students at Williams about this that I can share with you. So, bet $1 on red. If red, up $1. Else, how much are we down? Else, down $1, bet 2 on red. If win, up how much?
5.
So if we get to this point, how much do we have? We bet $1 on red.
You bet $1 on red. If you win, you get $2. So you're up
Yep.
$1.
So we're up $1. We've already lost $1. Right? To get to this point, we had to lose the first round. So I lost $1. I'm down $1. I bet $2. So I'm now plus $1. Else, how much am I down?
$2.
No.
You've gone twice.
I'm down $3.
Yeah.
I bet $1 and I lost.
Okay,
I bet $2 and I lost.
Okay.
I was down 3. Bet how much? $4. If win, what? I'm up. So how much am I up if I win? I'm up 1.
Right?
I also, but just look at the very last time. Else, I'm down $3. I've taken into account everything here. I'm down $3. I just made $4. Double plus 1. So the name hopefully now seems a little bit more logical. Every time you double your previous bet and you net $1, let's just do one more. Else, how much are we down? If we lost at this stage, we're down 7. Right? I was down 3, I bet 4 and I lost, so I'm down 7. And now how much do I bet? 8. I notice I'm not even bothering to write anymore if I'm betting on red or black. Doesn't matter. If win, how much are we up? $1. So keep going. Lather, rinse, repeat. Right? You keep doing this long enough, and you win $1. And we talked about memoryless processes earlier. These are extremely well-prepared, thought-out, unified series of lectures you're getting, right? We talked about memoryless processes. We've now won $1. it may not be reasonable to say that it's memoryless. Vegas does keep track of what's going on. If they see one person consistently winning, Vegas has a long memory. And they have little nice rooms where they can talk to you about mathematics. Very soundproofing so there'll be no distractions. So if it was truly memoryless, we would just keep doing this until we get to however much money we want to win. And we go home. So there must be something going on here. I mean, I love teaching, I love talking to teachers, but there's a reason I'm here and not in Vegas.
The green space.
I'm sorry?
The green space.
All the green space does is change how long it takes us to win. Right now, 50% of the time I'm here and I win, 50% of the time I lose. If there was a green space, all that would happen is it would take me a little bit longer to get to those places. So
Well, the probabilities of each outcome are different.
what do you mean?
Well, you've got, so it's 50-50, either going to be win or lose each round. Right?
Each round is independent of the others. And you know, if there were greens, it wouldn't be 50-50 anymore. It might be 52% chance of losing, 48% chance of winning. That just means it takes longer. So why am I not in Vegas?
The numbers?
I'm sorry?
The
A
numbers?
bit
What
possible.
about the numbers?
Like, I don't know how the rules are. Can you just bet red or green, or do you have to
You
have
can just bet. You
numbers
can just bet
involved?
red or green.
Oh.
Yep, that's fine. And in fact, one of the things Vegas does now is there are two major types of morons who play roulette. There are the morons who believe that a color that has just come up a lot is a lucky color and will bet on it. And there are those who believe that the color that hasn't come up is the due color and will bet on it. And they really don't care which type of moron you are, as long as you're a moron with money. And so Vegas will now display, I'm told, the results of the last few spins of the roulette wheel. Red is due. Black's on a roll. You know, they want you putting your money down. There are two issues. So what are the two issues?
Running out of money.
Running out of money. So maybe I've lost quite a few spins in a row, and now I'm at the point where I have to put down, $1 million. And if I lose, I then have to put down 2 million, then 4 million, then 8 million, then 16 million. So one issue could be you might not have enough capital to keep playing. You might have, if you get too many blacks in a row, you go bankrupt. So I introduced a new hypothesis. The ERU/A. It stands for the eccentric rich uncle/aunt. So you have a family member with unlimited funds who is willing to bankroll you. For some reason, because they're very eccentric, they will not give you any money directly to keep. So if you just ask them, can I have $1? No. Can I have $10 million to place on a spin of the roulette wheel? Sure. Okay, they're eccentric. But they will provide the financial capital you need for any bet. So you do not have to worry about running out of money. If you need $1 trillion to put down on the table, they will have that $1 trillion ready for you. Okay. Highly unreasonable assumption. But if I can convince you that you can't win the game, you can't beat Vegas, even with the eccentric rich uncle/aunt, then you should realize that it's not even worth playing when you don't even have the eccentric rich uncle/aunt. There is another problem. And for this you need to know a little bit more about how Vegas works and how roulette works. Just because you want to place a bet doesn't mean they'll let you.
No.
Vegas has max and minimum. So max and minimums at the tables. And trust me, they have done the math very well here.
Yeah. They're monitoring this.
Well, they know how likely is it to get 5 straight blacks and go bust. So they set the limits so that you could reach the point where even if you have the money to put down, let's say we've lost a couple in a row. So the first time we lose $1, $2, $4, $8, $16. So if we sum this up, we've lost $31. We want to put down 32, and maybe the maximum allowable bet is only $20. So the problem is, when you lose big. When you win small. And so if Vegas sets it up so that the spread from minimum to maximum bet at the table is basically a factor of 20.
So how common is that? Is it fairly common to have a limit?
Oh, Vegas always has a limit.
Okay.
Always.
Well, I mean, the bigger overarching idea here that probably anyone who teaches probability statistics gets to their students, which is that the laws of probability and the rules of probability don't really apply to you as an individual gambler, because you're operating in the very short term. And those limits that they've set up, that the casinos have set up, have been to protect them against many gamblers
Yes.
applying this strategy, but wouldn't necessarily affect
So for instance,
you individually.
if you are willing to accept the possibility that you might lose all your money, you can actually play double plus one and make most of the time a nice profit. But there'll be enough people who do this that there'll be a few people who will fail miserably.
And so the casino comes out on top.
The casino comes up on top. And so you could ask, if you needed to make a quick dollar, is this the best way to make a quick dollar? You have a huge exposure, because you could go belly up and you could lose everything. So when you lose, you could end up losing $31 to make $1. But maybe you have a really high probability of making that $1. Maybe you make that $1 60% of the time, 70% of the time, 80% of the time. So the question would be, how likely is it to get 5 consecutive blacks? And so what I'll do is I'll show you how to analyze that in terms of the Fibonacci numbers. And to show that this is all connected. So there's a video I've done of this online on YouTube. It's about 8 minutes, maybe 6 minutes. We're told that's about how long students can pay attention. I couldn't make it shorter than 6 minutes. But it goes through all the math of the Fibonacci numbers and applying it to the double plus one. So this is something that you can give people to look at. So I'm going to show you how to calculate the probability of getting 5 consecutive reds, or 5 consecutive blacks.
Is this assuming that there still are no greens?
I'm sorry?
This is assuming that there are no greens.
There are no greens. And so we could do the more general case of including greens. And so let's say, I'm not going to just keep the algebra simple on the board, but you can, in 1 minute, tweak this to allow greens. So, probability of a red.
Do the greens make it even third?
There's only 2 greens.
No, 2 greens.
There's only 2 greens.
Okay.
So
Out of what, 100 number?
out of 38, I believe.
Okay.
Probability of a black, we'll say, is P, and we'll say it's 1 minus P. And right now, we'll do P equals 1/2. But you could go through this and do the more general case of P and not just 1/2. So let's let AN be the probability no consecutive, no 5 consecutive blacks in n spins. And let's let Bn be the probability we have 5 consecutive blacks in n spins. So clearly, if I can find one of them, I can find the other, right? They can't both happen. And it turns out one of them is a lot easier to compute than the other. It turns out AN is easier to calculate than BN. So we'll find AN, and once we know AN, we'll then figure out what BN is. So we start here at AN. And then we have 2 possibilities. So actually, let me switch and I'll use green as my base color, so I can use color well. So here we go, we start off here, here's AN. We have 2 possibilities. We could get a black, or we could get a red. And so now, if I start off with a red, how many spins are remaining?
4. Oh no, 5. Were we trying to not get them?
I don't want to have 5 consecutive blacks and n spins. I've done my first spin. So how many spins are left?
At least 4.
To get not a string of 5 blacks?
Right, how many times am I spinning the wheel? I told you I want to spin it n times,
Yeah.
We're done.
Just 4.
4. 4.
not 4, n minus 1.
Well,
I need to spin the
number of
wheel
spins.
n times. The number of spins is n.
Right.
I've spun the wheel once.
And
How many spins are left? There's n minus 1 spins left to go. Okay? So I've already done 1 spin, so I have n minus 1 spins remaining. N minus 1 spins left. Anybody ever watch the TV show Press Your Luck? Renamed to Whammy?
Old, it's an old show.
It's an old show. There was somebody in the 1980s who recorded it on his VCR and noticed that as the lights, the lighted square went around, it didn't go around randomly. There was a pattern. And he won over $100,000 and set the record back then for largest single day winning in TV history. It was years before they would re-air the episode again. When you watch the video, he's actually celebrating before they announce the outcome because he knows what's happening. And so the events were not random. He actually saw the pattern that was going on. This is the hardest part of the analysis. I want to calculate the probability I don't have 5 consecutive blacks and n spins. That's AN. What's the probability I don't have 5 consecutive blacks and n spins, given that the first spin is red? So this is the hardest part. I want you to express it in terms of the A's and the B's. So how many spins am I doing? How many spins do I have left at this point? N minus 1. Could this red contribute to 5 consecutive blacks?
No.
So the probability of having no 5 consecutive blacks, given that the first one is red, is just
Starting over.
starting over, but now with how many spins?
N.
Not n.
N minus 1.
N minus 1. So what would the answer be? I'm sorry?
N minus 1 times AN.
Nope. AN means the probability of having no 5 consecutive blacks and n spins, and you're just multiplying that by n minus 1. You could have multiplied it by something that makes it over 100. The probability could have now exceeded 1. So A with the subscript is the probability I don't have 5 consecutive blacks in that number of spins. How many spins do I have?
So A to the N minus
It's A sub n minus 1. That's going to be the probability I do not have 5 consecutive blacks in my n minus 1 spins. Now let's look and see what happens over here. There are 2 possibilities. Right? I could be black. I could be red. What's the probability I do not have 5 consecutive blacks, given that my first spin is black and my second spin is red? A sub n minus 2. And then we keep going. Could black start a string of 5 consecutive? Yes. And so we have to keep going again. I always wonder why I use such a large number like 5. Here's black. Here's red. Actually, just to save a little time on writing. Alright, so here's my red. Here's my red. This will be AN minus 3, AN minus 4, AN minus 5. This is black. Oh, I'm running out of blackboard space. I'm hesitant to write any lower than this. Is it bad that I run out of blackboard space?
Oh, you got 5.
No. I have 5, no. What is the probability I do not have 5 consecutive blacks, given I start with 5 consecutive blacks? 0.
Yeah.
Right? That's why this is the easier problem to solve than the other one. Because at this point, the tree is dead. It's a finite tree. So now all I have to do is figure out what's the probability I'm in different parts of the tree. Well, the probability I end up here is 1/2. Here is 1/2. Each one of these is 1/2. So the probability I end up here is 1/4. The probability I end up here is 1/8, 1/16, 1/32. And so I get the following recursive relation. AN is 1/2 AN minus 1 plus 1/4 AN minus 2 plus dot 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 plus 1/32 AN minus 5. This is almost enough to solve the problem. I need some initial conditions. For the Fibonacci numbers, it wasn't enough to give the Fibonacci relation. I had to give you some starting values. Can anybody tell me what A0 equals? The probability you do not have 5 consecutive blacks, given that you spin 0 times.
What?
1. What about A1? A2?
One.
A3? A4? Okay, so actually the initial conditions are not so bad here. And so if you look at that formula, then this tells you A5 is 1/2 of 1 plus 1/4 of 1 plus 1/8 of 1 plus 1/16 of 1 plus 1/32 of 1. And when you add all of this up, you get 31/32. And if you think about it, if you spin 5 times, there's 2 to the 5th or 32 possibilities. The only time you would get 5 consecutive blacks is black, 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 black. So this at least allows you to check that very first next number is correct. So there's ways to jump and actually compute the 100th term in the sequence. And so if people are interested, maybe we'll talk about that next time. But here you can use this formula, and you can just use an Excel spreadsheet, and you can just march down and figure out what the 100th is. You just take this weighted average of the previous few terms. And Excel has beautiful formulas to allow you to drop down like this. And then you can actually calculate and see what is the probability you get 5 consecutive blacks in 100 tosses. It's about 80%. So 20% of the time you win $1, 80% of the time you lose $31, I think it is. And so when you lose, you're losing by so much, it overcomes the amount you win. Any questions about this?
I have a question.
Yes?
They have in Las Vegas, in the Bellagio Hotel, they have a war table. You know what war is?
No.
It's,
Oh, the game war?
yeah.
Yes.
And I feel like it's the same thing as that, except instead of doing black, red, you're doing high, low. And then, but I feel like it's the same idea as winning and losing.
You have more 52 rather than 38, right? No, they have multiple decks.
They have multiple
Yeah, they have
decks.
multiple decks, but it's still a 50-50 shot at
Right.
winning. Is it? Yeah, because it's you and the dealer.
It
Right.
depends on
Right, but if you have a 3,
there's lots of cards higher than that.
But the dealer and you are both likely to have that 3.
right.
So for each turnover, it should be 50-50. But if there's a tie, if you both turn over
I
3s,
think that's
does
where
the
they
dealer
get you,
win?
and that's where you lose.
And that's the small little
Yeah.
push to the dealer.
Yeah,
There's always something
that gets
What happens if there's a tie?
the dealer wins.
the dealer wins. So if you
You
both
don't
put
do
over
more?
3s, in a real game of War, then you would have another battle where you've done, you
The
put down 3
ties
cards.
will
Three and then you
Right,
Yeah, but
and
in
you flip.
this, in
They don't do
Las
that in
Vegas,
Vegas?
yeah.
No, they can.
It's like playing with a bias point. There's got to be, the phrase is, somebody has to pay for Mr. Smith's suits. There's got to be something that's giving Vegas the edge. And so in War, that's probably what it is.
Because the first night I won $900, and the second night I won and lost like $1,200.
You should have just walked away.
But I'm like, as a math teacher, 50-50 seems.
Right, it's not 50-50. And so the whole point, and we can talk about this, is to try to hide the true probabilities. Is to try to give a problem where the person is deliberately miscalculating the probability. So for instance, a lot of times if you look at lines for betting, the lines for betting do not reflect what Vegas believes will happen on the event. Vegas is trying to make sure half the money goes on one side, half the money goes on the other side of the bet. Vegas wants to be the conduit and just pass the money back and forth. And so if everybody bet the same way, you could break Vegas if you're right. So Vegas wants to balance the bets to limit their exposure. It limits their profit, but they would much rather have a guaranteed small profit than have a risk of going under. So I thought we would just end this unit by bringing it back to the Cam, Kayla, and M&Ms. So M&Ms, Cam, Kayla. So again, the full details are online if anybody wants to see it. I want to just do a very brief introduction so you can see how the stuff we've been talking about, recurrence relations, ties into something like this. All right, let's let x, c, k equal the probability of a tie if Cam has C and Kayla has K M&Ms. So I want to calculate this. So there are some cases that are really easy to calculate the probability of a tie. Can somebody tell me a situation where it's going to be very easy to find the probability of a tie? So some number of C, some number of K, where it will be very easy to figure out a tie. They both have, well, no, they both have one is not easy.
0.
One of them has 0. So x, C, 0 equals 0 if C is greater than 0. X, 0, K equals 0 if K is greater than 0. And if they both start off with 0 M&Ms, the probability of a tie is 1. So these are the conditions that are very easy to calculate at first. And now we want to calculate the other possibilities. So we're going to get a two-dimensional recurrence, unlike the one-dimensional recurrence. So how many of you have taught the Fibonacci numbers? Has anyone taught them to their students? So if you have some advanced students who are looking for some things, the Fibonacci numbers aren't too bad. I can give you some handouts. And then for anybody who's getting really cocky, you can try to show them how would you do a two-dimensional recurrence relation. I know formulas to jump to the nth Fibonacci number. It's much, much harder in this case. So let's say we start off with CK M&Ms. What are the possibilities that could happen 1 unit later? So one possibility is they both eat. What else could happen? One does, one doesn't. So it could be C minus 1, K minus, C minus 1, K. Could be CK minus 1.
CK.
Or it could be CK. And so if I look at it like this, what's the probability of the 4 events happening? Each one is 1/4. And I would get a recurrence relation. I claim, however, that I could actually look at only 3 events happening. Which event can I kill?
One that's in the middle.
Do you have any kids?
Yeah.
Okay, so if you have kids,
So
does
it's
it
like
matter which
specific-
kid has the M&M?
So it's specific, it's not just saying like one has one less, we're not looking at it that
I'm
way.
not looking at it that way.
Okay.
Cam has one less or Kayla has one less. Because remember, as soon as one of them goes down to 0, game's over. So it matters who loses the M&M. Which is the case I don't have to consider. CK. What happens if I get to this case? We said it's a memoryless process. So one possibility is I could keep this in, and I could have my recurrence relation with 4 things, and if you do the algebra, it'll reduce to a recurrence relation with 3. Or I could just say, screw that. Let's just forget about this to begin with. Because if that happens, I just go into these others.
Why can't we say the same thing about the first case?
Because this is a fundamentally different case. I now have it's not the same state. My state has changed.
That's not Larry and Magic who have just played for hours and we didn't see them?
No, because that'd be keeping track of who made baskets. So think of this as Kim just got a basket and Kayla just got a basket.
They started off with 5 basketballs each.
Right. And as soon as you make a basket, the basketball is gone.
Okay.
And so if you do it this way, there's 3 possibilities. Each one happens a third of the time. And this would give you the relationship x ck equals 1/3 x c minus 1 k minus 1 plus 1/3 x c minus 1 k plus 1/3 x c k minus 1. So in particular, x11, the probability we start off with 1 M&M each and we end up with a tie, is 1/3 x 0, 0 plus 1/3 x 0, 1 plus 1/3 x 1, 0. But x1, 0, x 0, 1, these are both 0. X 0, 0 is, so we've just calculated x1, 1 is a third. And now you got to do a lot more work. You can now try to figure out the x22s. Well, the problem is if you want to calculate x22, that could break into x21, x12, which you don't know. So the next one you try to compute is x21, which is the same as x12. And this would then be 1/3 of x11 plus 1/3 of x, I'm sorry, this would be 1, 0. They both lost a number now. 1/3 x11 plus 1/3 of x20. And so I'm not going to write down what it is, but you could see now that you could calculate x21 and x12. Once you know those, you can calculate x22, and you can keep trying to build like this. So you can solve more and more problems. And so the question becomes, is there a nice way to just jump to the solution to this? This seems a lot more involved than the Fibonacci numbers. And so while I know formulas to quickly jump to solutions for the Fibonacci's, here it's much harder and not quite as aware. So this was a fairly long unit, but there's a lot of good mathematics in this. And some of it is hopefully taking things your students have seen, but now looking at it in a new light. So a lot of them have probably seen the Fibonacci numbers. If you want to try to convince people about applications, there's a great video, Nature by Numbers, which I'll post, which shows you all these strange places where the Fibonacci numbers emerge. And so the question is, why do we want to understand these? Well, here's a bunch of examples. Here's some from biology. Here's some from gambling, from roulette. And so really, the Fibonacci numbers are an example of a difference equation. If you've taken differential equations in college, difference equations are a discrete version of differential equations where just time moves in fixed increments rather than continuous increments.
How long do you allow your kids to play around with stuff like this?
My kids or my students?
Your students.
My students. That's the problem. It's the hourglass always being emptied. And so I will know more in 3 months. I will stop recording now so I can speak a little more freely. We're experiencing